Hello people. Today we will study how to implement recommender systems using ALS or altering least squares in Spark. A recommender system or a recommendation system is a platform or engine predicting the rating or preference that a user would give to an item. Recommender systems are considered as the most successful and widespread applications of big data and machine learning technologies in business. This type of systems are used in various areas to match users with the most appropriate contents and products. For instance, recommender systems are widely being used by online content providers such as YouTube to create personalized playlists based on the user's taste. Or online retailers such as Amazon recommends desirable products based on the customer's interest. Generally speaking, recommender systems are using two main strategies: content filtering or collaborative filtering. In the content filtering approach, the system creates a profile for each user or product to characterize its nature. For example, a movie profile could include attributes such as its genre, the actors starring in it, and so forth. User profiles might include demographic information or answers provided on a suitable questionnaire. Using these profiles, the system matches products with appropriate users. However, it is obvious that this approach requires gathering external information that might not be available or easy to collect. Collaborative filtering is an alternative approach to content filtering. This approach needs no explicit profiles and only relies on the past behaviors of users, such as user ratings, watched videos, visited products, and search patterns. This topic is a huge topic, and in this module, we attempt to cover collaborative filtering because of receiving a lot of attention, and there are various open source implementations, including implementation in Spark. Collaborative filtering considers the actual ratings made by all users to find similarities between users' interests and preferences. In other words, this approach gradually collects preferences or taste information from many users to make automatic predictions about the interests of a new user. The underlying assumption of this approach is that if person A has the same opinion as person B on a given item, such as a movie, user B is more likely to have user A's preference on another movie than that of a randomly chosen person. For instance, in this example, user A and B both like the first movie. Based on this information, it can be concluded that user B highly likely dislikes the second movie because user A has given a thumb down rate to this movie. Therefore, collaborative rating allows us to predict the rate given by user B to a movie that has not seen yet. This slide visualizes a collaborative filtering recommendation system for television tastes. In this example, rows correspond to viewers and columns represent the TV programs. Each cell determines the preference of a user about a TV program, which is either like or dislike. For instance, user number 1 likes the movie but dislikes this documentary program. The goal of this system is to predict a given user preference about the movie based on previous users' taste. To create such a recommender system, in the beginning, the system gradually collects the likes and dislikes of some users. Then it creates a model to predict the taste of user 4 about the movie. Upon the existing rates of other users, user 2 and 3 have similar ratings with the active user 4. Since these two users didn't like the movie, it's predicted that the active user 4 won't like the video. Please note that this prediction is specific to the user, but uses information collected from many users. Here we have another example. Joe likes the 3 movies on the left. To make a recommended playlist for him, the system finds similar users who also liked those movies. Based on this information, the system determines which other movies they liked. In this case, all 3 users liked Saving Private Ryan. So, that is the first recommendation. 2 of them liked Dune. So, the next movie recommended by the system is the movie Dune, and so on. In previous examples, we didn't characterize users and items. In fact, we made trivial predictions only upon the like and dislike information of users. Now, I want to introduce a more general and powerful method that tries to explain the ratings by characterizing both items and users using some factors, which are inferred from the rating patterns. This method is called latent factor. In this approach, we have a set of factors ranging between 10 and 100. For any specific factor in the set, the factor determines how much an item passes that specific factor and how much a user likes or dislikes that factor. For instance, consider a given factor seriousness. The seriousness of a movie can be expressed as a number based on its content. Please note that the factor value might be a positive or negative number. In other words, the more serious the movie, the higher the factor value. On the other hand, users can express their interests in serious movies using a number, either positive or negative. Then this factor, along with any other factors, are used to predict the best matches between users and movies. In this slide, we have an example, including 2 factors characterized as female versus male oriented and serious versus escapist. The figure shows where several well-known movies and a few users might fall on these 2 dimensions. As we can see here, users and movies are characterized using these 2 factors. In this model, the predicted rating of a user for a movie is equal to the dot product of the movies and users' locations on the graph. For instance, the factor vector for gas consists of 2 numbers, each for 1 factor. Similarly, the movie Dumb and Dumber has a specific vector with 2 factors. So, to obtain the predicted rating of the movie Dumb and Dumber by Gus, we should dot product these 2 vectors. Therefore, in this example, based on this factorization, we would expect Gus to love Dumb and Dumber. to hate the color purple and to rate Braveheart about average. Please note that some movies, for example Ocean's 11, and users, for example Dave, would be characterized as fairly neutral on these two dimensions. Now you might ask how we can computerize the latent factor method to predict ratings. In the previous slide, I explained the latent factor method by an example including two factors or dimensions. Let's consider a more general case with f factors, where f is usually an integer number between 10 and 100. We define u as a vector of f real numbers. This vector determines the preference of a user for each factor modeled by a real number. This number can be positive, 0, or negative. For instance, in the previous example, if the preference level of a user to serious movies is a positive number, it means that that user likes serious movies. The greater the positive number, the higher interest in the serious movies. However, a negative factor value represents the user hates serious movies. Similar to users, we also define another vector m including f factors. Each factor for an item represents the level to which the item passes the factor. Each factor for an item represents the level to which the item passes the factor. For instance, in the previous slide, the seriousness factor for the movie Braveheart is positive, but it is negative for Dumb and Dumber. So, we have two vectors u and m. The former characterizes a user and another one factorizes an item. The rating that a user would give to an item is calculated by the dot product of these two vectors, which is a single real number. If vectors u for all users in a system are stacked up, and vectors m for all items in the system are put together, we will have two matrices. Matrix capital U have factor vectors for all users. Each row in this matrix corresponds to a given user. Matrix capital M determines factor vectors for all items. Each column in this matrix corresponds to a given item. If we multiply these two matrices, the result matrix R determines the predicted ratings. For instance, here we have matrices U and M for a platform including 6 users and 9 items. If the vector number 3 in U is multiplied by the vector number 5 in M, the result is a single number in R, which is highlighted in blue. This number represents the predicted rating of item 5 by user 3. In the same manner, we can obtain the predicted rates for all users and items. In real platforms, the major challenge is how to compute the mappings of each item and the mapping of each user to the factor vectors. In other words, we don't know matrices U and M in advance, but we do know a subset of actual ratings submitted by users. One technique is to create the factor vectors using the ratings submitted by users. So, a recommender system in the beginning records user ratings to obtain some elements in matrix R. Then, the system creates a model by filtering the previously recorded ratings to model matrices U and M. The fitting process models matrices U and M so that the difference between any predicted rating in matrix R and its corresponding actual rating is minimum. After modeling the matrices U and M, the recommender system can predict the user ratings as explained in the previous slide. Modeling matrices U and M is an optimization problem. To solve such an optimization problem, one solution is to employ stochastic gradient descent techniques, which are used for training artificial neural networks. Another solution to address this minimization problem is to use the alternating least squares or ALS technique. In this module, we only focus on the latter technique, which is ALS. Since both M and U matrices are unknown, ALS chooses a random starting point for M and finds the best U based on the random values for M. Then, with the new values for U, the algorithm finds the best new values for M. We iterate these two steps until convergence. Please note that the detail of the ALS optimization algorithm is outside the scope of this module. However, in Lab 5, we will use the ALS technique to build a sample recommender system in Spark. In this slide, we have 3 papers for further reading. Okay, this brings us to the end of today's lecture. Thanks for watching this video.